Alright everybody, welcome back. In this video we are going to handle content from section 9.7 of AP Calculus BC, defining polar coordinates and differentiating in polar form. Alright, so we start here with a basic definition of polar coordinates. Polar coordinates can be represented as an ordered pair. Sometimes you'll see with polar coordinates the P in front to let you know that it's polar coordinates instead of a Cartesian ordered pair. A lot of times though we're really using context when we're talking about these ordered pairs. But these are the two coordinates, r and theta. R is the directed distance from the origin, or O, also known as the pole, to P. Okay, and theta is the directed angle from initial ray to ray OP. I should probably have justified this and pushed it over here. My bad. I'll fix that formatting. Anyway, so theta is the directed angle from the initial ray to the ray OP, and r is the directed distance from the pole to this point P. So let's see, we've got a pole and an initial ray, then all the points in the coordinate plane can be represented by an ordered pair r, theta. Something important for you to know about polar coordinates: unlike Cartesian coordinates, polar coordinates are not unique. If I give you the Cartesian coordinates 5, 3, that's the only pair of coordinates that I can use to represent that Cartesian point. Whereas on a polar grid, there are going to be an infinite number of ways that we can write them due to the cyclical nature of the angle, and also due to the fact that we can have a positive or a negative radius. And, if I have a positive radius and then I take the negative radius with angle that differs by pi radians, I end up at the exact same point. It says here, for instance, the point 2, 7 pi over 6 can be represented with a number of other polar coordinate pairs. For instance, the point 2, 7 pi over 6 is like right over here, somewhere where this radius is 2 units and the angle is 7 pi over 6. Well, if I go around the circle again, around the unit circle, this can also be represented by the ordered pair 2, 19 pi over 6. Or it could have been represented by the ordered pair 2, negative 5 pi over 6, where we go backwards to get to that point. Or, in fact, it could be represented by this ordered pair, negative 2, pi over 6, where we go with a pi over 6 angle, but we're going 2 units in the opposite direction, which gets us to this point. So there are literally an infinite number of polar ordered pairs that we can use to represent any given point in the polar coordinate plane. All right, let's do a couple of graphs here, just to get us introduced to graphing in polar coordinate. Most of the time in this class we're going to do any graphing that we have to do of polar coordinates by hand, or we might have a graph provided for us. But it's good for us to understand how we graph in polar coordinates. In example A here, we're going to draw two curves on this same grid. These are the two special kinds of curves. In Cartesian coordinates, when we have a line like x equals 5, we should all know that that's a vertical line. That's one of the special curves in the Cartesian graph. And then, if I have the line y equals negative 2, that's a horizontal line. Again, that's one of the special lines in the Cartesian graph. On the polar graph, there are two special kinds of lines. One when we have r equals some number, and one when we have theta equals some number. R and theta are kind of analogous to the x and the y as the two variables that are, our coordinates in the polar system. So let's talk about what these graphs look like. The graph of r equals 5 is telling us to plot all the points where the radius is 5, no matter what the angle. And so on this polar grid here, I'm going to go out to where the radius is 5, and usually we'll use the rings here to be our units. Sometimes we might number them differently, but basically r equals 5 is going to be a graph of all the points on this ring. because those are all the points that satisfy the polar equation r equals 5. Don't mind me, I'm a little sketchy and didn't do a real nice job drawing that circle. But that's the graph of r equals 5. And then the other possible special kind of graph is when we have theta equals some value. So theta equals pi over 6, that's going to represent all the points where the angle theta is pi over 6. So like here's the point 1 comma pi over 6, and here's the point 4 comma pi over 6, and here's the point -3 comma pi over 6, and you quickly find that those points all form some kind of line, a line that forms an angle of pi over 6 with the initial ray. And so there's the graphs of what r equals 5 and theta equals pi over 6 look like, some of the special graphs. Now in part B, we're going to draw the graph of r equals 1 minus cosine of theta. In order to do this, I'm going to change our scale on this graph a little bit so that it's easier for us to graph and easier for us to read. We are going to define each ring in this graph to be equal to 1/4 of a unit. Okay, 1/4 units. So like, I'm going to put some black marks on here. That's 1, 1. I'm going to do that in all the directions. So the darker marks mark 1 and 2, the rings that represent 1 and 2 units in this graph. All right, now in order to graph this by hand, what I'm going to have to do is I'm going to have to cycle my way through theta values for the angles in order to plot various points. So I'm just going to go through and take the common theta values that I know the value of cosine for, substitute them in here, and then approximate the value of r in order to graph this. So we start with an angle of 0, so the angle going this way. And if I substitute 0 in here, cosine of 0 is 1, 1 minus 1 is 0. So for this angle, the distance from the pole is 0 units. And so that's the point that represents the polar pair 0, 0. The next angle that we all know is pi over 6. The cosine of pi over 6 is the square root of 3 over 2, which is approximately 0.866, which means 1 minus that is approximately 0.134. These circles, remember, are a quarter, so it's going to be a little bit more than halfway to there. And I'm going to plot that point along the angle pi over 6. So a distance of 0.134 from the center along the angle pi over 6. Okay, next one, pi over 4. Square root, cosine of pi over 4 is square root of 2 over 2. Square root of 2 over 2 is about 0.707. So this is about 0.293, a little bit more, and that's going to be on the angle pi over 4. We'll plot that point. And then at pi over 3, cosine of pi over 3 is 1/2. 1 minus 1/2 is 1/2. And so at the angle pi over 6 from the original ray, our length is going to be 1/2. Pi over 2, cosine of pi over 2 is 0. 1 minus 0 is 1. And so when we get to an angle of pi over 2, the radius is 1. We'll plot that point there. And we keep going around the curve in that same fashion. 2 pi over 3, the cosine is negative 1/2, so we'll have a point at 1.5. 3 pi over 4, it's square root of 2 over, negative square root of 2 over 2, so that's like 1.70-ish at that angle, so somewhere around here. And when it's 2 pi over 3, we're over here, that's going to be 1.866, so somewhere in this neighborhood, and then 2. And then I'm going to use what I know about the symmetry in my unit circle to come up with the rest of these points very quickly, because the cosine value is the same quadrants 1 and 4 are the same, so the points plotted in quadrant 4 will be a mirror image of these points, and the points plotted in quadrant 3 will be a mirror image of these points. So I'm going to go ahead and use that to my advantage to more quickly plot the rest of these points around the graph. And we're almost there. And now I can connect these points around. And by the way, once I get to 2 pi as my angle, wow, that's really bad on my part there. I got really flat going around that curve. This is hard to do on my computer because of the angle that my hand has to go to sketch these curves. But I'm doing the best I can here. All right, and there is roughly what the graph of r equals 1 minus cosine of theta is going to look like. And if I went for theta values bigger than 2 pi, it would continue looping around this graph. Let's take a look at what this looks like on my calculator. All right, I'm going to go to polar mode. And again, when we change our mode, it's going to change the window of our calculator a bit. I'm going to change these to -2 and 2, since that'll match my grid that I have. And I have it set up from 0 to 4 pi, or 2 pi, since I knew that was a complete rotation. And we're graphing 1 minus cosine of theta. And I'm going to, just like I did with parametric functions, I'm going to graph with the path so that I can see the curve going around. And here we go. Here's our graph of 1 minus cosine of theta. Now realize this is distorted because of the fact that the width on the calculator is wider than the height. So what I can do to get this to look more accurate is I can go ahead and zoom square, and that'll give me a more true to real life picture of this. And you see how close this is to the graph that we drew by hand. And remember I said if we had, extended the angle even further, maybe I could extend the angle instead of going from 0 to 2 pi. Maybe we could graph this from 0 to 6 pi. And you see that all that happens if we do that is that we draw the graph, and when we get to the end of the graph where the two pieces meet, the graph will just retrace over itself as it goes through the rest of those values from 2 pi to 4 pi and from 4 pi to 6 pi. All right, so that's a start, an introduction to polar graphing and polar coordinates. Like I said, for the most part for our class, if we need the graph of a polar curve, we are going to look at it by using our graphing calculator. So make sure you get familiar with the settings in your window and your y equals screen for polar graphing. All right, we're going to call it a day there, and we'll come back with some more videos, probably 2 more videos on this topic, because I don't think I can fit it in one. But we'll see. So see you next time when we come back for video number 2 on defining polar coordinates and differentiating them. All right, have a great rest of your day, everybody. See you next time. Bye-bye.